Let's move on to the 5-membered rings. We've done a lot of aldohexoses and saw their Furanose forms when they're closed in a ring. When we have a 5-membered ring, sugar, what are we going to call it? We know this without knowing it. So let's see where we get the information from. So a couple things. We're going to use D-ribose as our example. We close it into a ring. It's going to look like this. It's a 5-membered ring. So let's number that first. We always know that the aldehyde carbon has to be carbon 1 because that's our electrophile, the one we attack, just to get our ring count. 1, 2, 3, 4. Now we need a 5th atom for the ring, and it has to be an oxygen to attack that carbon to make that hemiacetal, right? So 5. There's our 5 atoms that make up the ring. Now it's not a cyclopentane because we have an oxygen in it. It's an acyclic ether. But we've actually named 5-membered heterocycles that are 5 and 6-membered with nitrogens and oxygens way back a long time ago. So I'm going to remind you of one cyclic ether we've used frequently. It looks similar. That's THF. And what does THF stand for? Tetrahydrofuran. Furan. The tetrahydro comes from the fact that it only has 4 H's instead of 8, but because the furan is simply that, has 8 H's when it's fully saturated as a ring. So this is furan. So a 5-membered ring with an oxygen is a furan. When it's a sugar, part of a sugar, carbohydrate, then it's a furanose. It's that -ose suffix. Couple things to point out. We have D, so we have the CH2OH up for D. We have beta because the OH that's part of the anomeric carbon is up on the same side as the CH2OH. Look at this interesting feature here. We have an X. That does not mean halogen in this case. It just means it's variable. 2 very famous bio-relevant, bio-crucial molecules, carbohydrates, have this exact structure, but they only differ by this X, what happens at X. So X is either OH, which is our usual expected scenario for a carbohydrate, or an H. That is not our usual expected scenario because remember, carbohydrates means every carbon has an OH. And so somehow the H is removed, the OH is gone and the H is in its place. So I'm going to give you the names of those two because they're ones you know and heard of before, and you'll kind of see that connection very shortly. So let's give the full name. When the OH, let's say we have OH as our X value. The product is beta, D. You always include those descriptors. Ribo, the prefix to tell us which sugar it was. Furanose. Ribofuranose. Is that an example? Ribofuranose. Ribonucleic acid, right? RNA. So you can guess its counterpart where X is not OH when X is H. So let's do that, and I'll do one in red. When X is H, our name is going to be the same almost, beta. Actually, it has another, it goes in front. Let's see. The description, deoxy, because the OH is gone, the H has taken its place. So deoxy, beta, D, then the rest is the same. Ribofuranose. So you've taken ribofuranose and you've deoxygenated it. This has actually happened enzymatically. So if this has happened where an enzyme has replaced the OH with an H, that is the ribofuranase missing an oxygen there. Deoxyribonucleic acid, right, is where we find this biologically. So we're going to take some time to look at DNA. It has some very interesting 3D structural features as well as molecular features, and I know we've looked at it many times. It has a lot going on there, and it's beautifully complex and simply elegant at the same time. But yeah, we've looked at the base pairs, how they hydrogen bond, and what's a hydrogen bond donor, etc. We've seen the pi-pi stacking interactions in our aromatic section. So way back in intermolecular forces, organic 1, we looked at the base pairs lining up. Beginning of organic 2, aromatic pi-pi stacking. Now we're going to look at the backbone. And we know that thanks to those offset pi-pi stackings, it does not let them line up like the base pairs line up like a rungs on a ladder. They get offset, and that offset helps create the twist. Now, what else is going on in that backbone? That's where the sugars are. So that's where we're going to hone in this time. So when that's twisting. And furthermore, what's a consequence of that twist? Well, why is it important to know that? So notice I've mentioned that we have this twist. You don't want to get in this situation. These snarky scientists like to blast these find errors in bio ads, and I admit it's amusing, but I want to point out that it's kind of a shame that a lot of money was probably put into making that graphical image or time, and it was given to a U.S. Department of genetic sequence data. So they're using this image to look very sciencey, but a snarky scientist calls them out with left-handed DNA Hall of Shame because we just only use the right-handed DNA. And what does that mean? It means, yes, DNA is chiral. Not because it has stereocenters. That's point chirality. It's chiral, just the shape of it's chiral. And that's a topological chirality. It's chiral nonetheless, though. You can draw an enantiomer of DNA's topology. So that's its shape. So let's look at this. This is a nice analogy. Remember, enantiomers aren't exclusive to molecules. Your hands can be considered sort of like enantiomers. Gloves that are directional, like those texting gloves that have the pads, they wouldn't, if you put them on the other hand, they'd be going the wrong way. So stairs, this is the enantiomer of this pair of stairs. This is from a contractor's website to, I guess if you were going to go build a beautiful custom home with these spiral staircases and you had to pick, do I want my stairs to start on the left, so space on the right, or do I want to go this way? That is a crucial decision in the construction as well, because that takes up a different type of space. And so these are actually enantiomers. So if they're enantiomers, if I pick that one up, that would not superimpose. So what is the descriptor for spiral enantiomers? We call that helical chirality. And with helical chirality, I'm just going to write that right here, helical chirality. So our body, as you could see from that snarky joke before, only uses right-handed DNA biologically. So it's not to say we can't make left-handed DNA. That's just not what occurs naturally. Be kind of a cool premise for a sci-fi novel, though, right? So yes, a whole universe where the amino acids are the enantiomeric form and your DNA. It might be less interesting, it might just be mirror images, but what would be the consequence of merging them? We could go on and on. Now, staircases are a good analogy because you can see that you can climb to the top of a spiral staircase, look down and see, you can see it wind. And if you see it wind in a spiral clockwise versus counterclockwise, then you know you have two different ways to describe it. So imagine going down this set of stairs, for example. So you're going down, and just imagine which way the clock hands would turn if you had to trace your path down on a flat piece of paper. So think about that. Okay, got an idea? Okay, So as it's going, I hope you came up with counterclockwise, which would mean this is exactly the opposite. But you know what? It's hard to, that's exactly how they decide the helical chiralities, to take the helix you're in question, not just DNA forms helices, other molecules do too, and look down the center and see whether it's going clockwise or counterclockwise as you traverse down. But you have to have the top as the right point of reference. And so that could be difficult to remember sometimes. So it's usually the 5' and the 3' end on the correct orientation. And what is that? Where did that come from? You probably learned a little bit about that in biology. We'll get to that too. So you first have to make sure you have the correct point of reference, because clockwise from one direction is counterclockwise from the other. Furthermore, if you have a hard time seeing the spiral, you're not alone. A lot of people, I think, would. The directionality of it. The nice thing about DNA is it has these kind of rungs that twist around this and held by the two sides. And so if you were to imagine going, as long as you have the orientation correct, if you say, what if I climb up the stairs? Which hand do I use to hold the rail? Okay, so you would use the left hand. That's your left hand, right? And every time the rail passed through the front, you would eventually start to see, if I continued the staircase, you would see it that way, right? And if we could continue this further down, it would go that way. And so they kind of lean, all of the rails that are in the front lean to the left. Likewise, if you were to go up this staircase and you held on with your right hand, right? And so any rails that pass in the front, so let's see if we continue that down and go up, they all lean to, well, as I do this on the video, I realize I have to do this probably here, right? So they all lean to the right versus the left. Okay, so that might be something to help you out if you're not seeing the clockwise. You know, you don't have to do both analyses. I like to actually just use it as a double check. So let's take a look at what that means here then. One more. I have a problem for you. Let's look at those DNA strands. Those are clearly enantiomers. Which one is left-handed? And which one is right-handed? Because we have to have one of each since they're mirror images, right? Think about that. Did you get an answer? How about we bring back the Hall of Shame? Well, if we know that's wrong, that matches this one over here, right? You see that? See how those lean to the left and these lean to your left? So they're going the same parallel direction. This must be the left-handed one. Or if I was going to say, I'm going to go up the DNA stairs. I'm going to hold on to the left side as I walk up. Or I'm going to go up the DNA stairs. I have to hold on to the right side as I work my way up. Right? Okay, so left is actually the one that's on the right, and right is the one that was on the left. Just to make it a good problem to think about. Okay, I hope you can do that. You'll need to be able to recognize left-handed chirality versus right-handed chirality in DNA. With it oriented, notice how there's always a 5' and 3'. They're always opposite. So that means that one of the strands, if you want to call one of them the tail, it's meeting up with the head of the other. They're going the opposite direction. Anti-parallel sort of arrangement. What does that mean? We can actually, the sugars explain that 5 and 3'. So if you've read about that and always wondered, I don't know what that means, I don't need to worry about it. Eventually, of course you do. And this is the time. Here it comes. So here's one strand, a short segment. I want, by the end of this discussion, us to label where the 3' end is, where the 5' end is. Okay. I also want to take a look at just what else goes into the structure and describe it a little more thoroughly. So this is the molecular orientation of it all. So just to give us a little heads up, I'm going to give you a preview of kind of what the answer is when you have both strands together. Okay, so let's zoom in on the structure. Look at how this is called the 5' end. This is called the 5' end down here. So we notice it's really not about the phosphate. The phosphates link up. They link up each sugar. So it goes phosphate, sugar, phosphate, sugar, phosphate, sugar, right? Sugar, phosphate, sugar, phosphate, sugar, phosphate. There's our base pairs doing their hydrogen bonding thing. We know that they do, right? There's also some less obvious pi-pi stacking. And so our phosphate deoxyribose backbone. Notice that they're anti-parallel, as I mentioned. 3' is on for one strand, which is opposite where the 5' is. So how do we determine really where does this 3' and 5' come from? It comes from the numbering and the nomenclature of carbohydrates. So let's do that. We are going to number this ring. We're going to start our numbering in a very specific way. It's not just for, usually we're numbering willy-nilly however we want so that we can use it as a reference or making sure we don't drop carbons, but this is for nomenclature purposes, which means we need to be pretty precise with it. So we're going to give carbon 1, which is actually the carbon we've been giving is 1, the one that used to be an aldehyde. So the one that used to be part of diacetyl, the anomeric carbon. Notice it's all gone. Like the OH has been replaced by a base pair. This has H's here because it's deoxy. There's no OH, deoxy. And then the OHs here are no longer OHs, they're O-phosphate. So they've all been put to use, to good work, right? So let's number around the ring. 1, 2, 3, 4. And instead of 5 on the oxygen, because we're not trying to count the number of members in the ring, we're counting the carbons that are part of this ribose. 5. And when we do this, we're going to do a prime number. 1', 2', 3', 4', 5'. So notice that the anomeric carbon is 1', and the carbon that's part of the CH2OH is the 5'. Used to be CH2OH, the former CH2OH. It's actually no CH2O-phosphate now. Okay, so now we're numbering. A couple other things. If we keep numbering, let's do it on each of them. 1', 2', 3', 4', 5'. 1', 2', 3', 4', 5'. Now, how do we know the 3' versus the 5' end? Look at what's happening here. The way this keeps going, it's connected to the 3' carbon. So we have the 3' kind of downstream, if you will. So this is the 3' end. Notice the highest carbon in this strand of all of those that we numbered, 1 through 5', is the 5' carbon. So that means whoever it's going to pair up with has to be flipped upside down. Okay, so those are some things to note there. I also want to point out that it retains that beta relationship. See how these are cis? Right, that part didn't change. And now we see the big picture. We see the base pairs. This is adenine, which is a purine. This is thymine, which is a pyrimidine unit. And we go to guanine, which is another purine unit. Okay, so I think I accidentally answered another question for you. Is it the alpha version or the beta version that is found in DNA? Yep, you got it. Right? Beta. Okay, so I hope you feel good about the topology, the way the DNA double strands arrange into a helical conformation, as well as the backbone, and everything we've learned thus far about base pairs and so on. Okay, so what is interesting here is that we, like I said, put those OHs and CH2 groups to good work. They made bonds. They didn't stay separate monosaccharides. So one of the most important bonds that carbohydrates make was encapsulated in a previous chapter. This is cut and pasted from there. It's just the formation of an acetal from the hemiacetal. So just in closing the ring, we arrive at the hemiacetal. But then, so let's actually draw that part out. So we have our aldehyde, right? And we go 6, 5, 4, 3, 2, 1. And I might even number this the other way. 1, 2, 3, 4, 5. And you need a 6. And that 6 is going to be the OH to make your 6-membered ring. So this was an equilibrium. We've done that. We closed the ring. And this is leaving out all the extra OHs. So right now it just looks like an internal hemiacetal formation. But that's what happens with carbohydrates, right? It's just that you have lots of other OHs on there. So when you first close, you have a hemiacetal. And this is an equilibrium. It could open back up to the aldehyde, which can actually do other reactions like get reduced or oxidized and whatever. But if you add more alcohol in some form, which could be another carbohydrate, another one of itself even, right? Then you form the acetal. And yes, this is an equilibrium as well, but it's far away from the original aldehyde it came from. We have a term for this. Once a carbohydrate has arrived at the acetal destination, so we've so far looked at lots of hemiacetal carbohydrates. Once a carbohydrate makes this bond with an additional alcohol, which is usually an additional, but not always, carbohydrate, it's an acetal, and we consider it more or less locked. We'll say it's a non-reducing sugar. Which means that the hemiacetal is actually reducing. So in either form, whether it's straight chain or not. What does that mean? It means it can get oxidized. It could be a reducing agent. There's actually an old qualitative test, like Tollin's test, by the way. One of the best aldehydes to use for Tollin's test is a glucose. So if it's hemiacetal in the ring form, that means it can open up and it's in equilibrium with its aldehyde form, straight chain form. If that is exposed to an oxidizing agent, it will reduce that oxidizing agent. Hence, it's a reducing sugar if it does that. So you can do a test for it. That's where the term reducing comes from. It's another way to phrase, do I have an acetal or a hemiacetal? If the answer is yes, I have an acetal, it's non-reducing sugar. If the answer is I have only a hemiacetal, then it's a reducing sugar. Okay. I'm going to spell that out one more time because sometimes that's a little confusing. So aldoses are reducing sugars because they can have the RCHO exposed to an oxidizing agent to make RCO2H. So if you have the aldehyde or hemiacetal, it will react with that oxidizing agent. So it's a reducing sugar. Okay. Something else to point out is because it is such an important bond when two sugars come together to make an acetal, we have a name for that bond. It's called a glycosidic linkage. Because you're going from a monosaccharide to a disaccharide. So it's a significant glycosidic linkage. So we're going to start looking at glycosidic linkages, which means we're moving beyond monosaccharides. Let's look at some disaccharides now. This one's called maltose. Okay, so let's look at a few features of maltose. The top ring and the bottom ring don't have to be the same sugar, but let's see if they are. So if I work my way around, I have my oxygen, and then my CH2OH is over here on the left, and below it I have the anomeric carbon. That's kind of the standard way to orient this. So my anomeric carbon has the OH, and then I have equatorial, 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 equatorial. By the way, when something handy to remember about glucose is when it's in its chair conformation, of course this is the variable one, but everything else is equatorial. All other non-variable H's in the chair are equatorial, which is one reason we kind of like using the chair so much, because there's so many glucose units. If you see all equatorial, you know it's glucose right away. So if it's, remember, if it's alpha versus beta determines how we're handling the anomeric carbon. So D-glucose has this one equatorial here, the CH2OH. Oops. There we go. So D-glucose has all of the OHs, or all the groups, equatorial. And it's going to especially be equatorial if it's beta, because you would have this is the only one that's variable. Okay, so we can see we have a glucose here. And then I have equatorial, 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 and then that's variable, so that's okay too. So I have a glucose here. So it turns out that maltose is made of two glucoses that connected together. So in other words, I'll take my glucose, and I have, looks like I was using this alpha version, right? Because the axial is in a different trans orientation than the CH2OH. And then I have the rest. So it's not always variable, but in this particular one. So in other words, if I take away water and I add two of those together, two equivalents, and of course this can be done enzymatically, but that's the idea of the chemistry that's happening there, then these would join at this carbon. And notice where it links up. It didn't link up on the other anomeric carbon. So it linked up on another one. So let's draw the other one out. Okay, so where did we lose the water from? Let's number around the ring and see if we could describe this. Carbon 1 is the hemiacetal or acetal carbon. 1, 2, 3, 4, 5. Okay, now let's go to the next ring. And to distinguish between them, I'll start using prime. 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. Okay, there's our linkage right there. This is where they connect. So that is called a 1,4 prime linkage, glycosidic linkage. Furthermore, notice how the linkage itself, this is an up group. This is a down, This is a down group. That tells us it's alpha, right? So alpha 1,4 prime. So we could have a beta linkage that's a 1 something prime, or we can have an alpha linkage. Let's give it the full name now with the names of the linkages, because we're going to name a disaccharide for the first time, and it's long. So we're going to start way on the left to give room. So name. Alpha dash 1,4 prime dash D, we already worked that out, glucose and glucose. So 2 glucoses. We're going to indicate one of them is the substituent. So we're going to say glucopyran because it's in a ring. Os, instead of os, it's going to be osil because we always put il to indicate the substituent. And then we're going to let one be the parent, D-glucopyranose. So that was a mouthful. I'm going to move that up so we can see it in all its glory. There we go. So one is the glucopyranose is connected to another glucose, so we call that glucopyranosyl. They're both a D. Alpha 1,4 is where they linked up. Maltose is actually a sweetener. Not as common in America. I know other countries use it. It's a little less sweet, than sucrose, so it's favorable for those types of sweets. But so clearly we could digest it. So alpha glycosidic linkages is something that mammals can easily digest. Let's look at another disaccharide that's beta, because what would that look like? Because the nature of the glycosidic linkage could have different numbers. It could also have different orientations, alpha versus beta. This is lactose. You might have all heard about someone that's lactose intolerant. It might be you. So lactose intolerance comes from lacking the enzyme lactase. What does lactase do? It does what we were doing in a flask with super concentrated acid to hydrolyze it. It breaks it down into its component pieces. So lactase would just break it down specifically, not just its pieces, but it specifically snips that glycosidic linkage and you get your 2 sugars back. Go from a disaccharide to 2 monosaccharides. The 2 monosaccharides are nice and small and easily absorbed into the body from the small intestine. So by the time it gets to the small intestine, if you've got lactase, sufficient amount of lactase present, then you will break down these 2 sugars into their component monosaccharides. But what are those monosaccharides? That's what we have to identify. So let's do that. Okay, I could see right now, it's not glucose. See that axial OH? That's not an anomeric carbon. There's no way that would happen on glucose. But this one, equatorial, 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 that's glucose. So you'd either have to look this up or say which one is which I think is easier. If I know this is carbon 1. And let's actually go ahead and number it because we need to number it for the naming system anyway. 1, 2, 3, 4, 5. So if I know this is carbon 1 and I have and I'm off at C4, a C4 epimer. Everything else is the same as glucose except that carbon. C4 epimer of glucose. We've actually looked at that one before. It's galactose. So lactase, when it encounters lactose, it comes and snips right there at that glycosidic linkage and does its karate chop in a very complicated way. And so we don't have mechanisms and arrow pushing for that, but we know what that would be if it was hydrolysis, right? We've done that before. So we have I'm going to draw galactose now. So just make sure that's an axial OH there, but the rest looks like glucose where it's equatorial. Actually, I'll just put the plus what? So that's galactose plus glucose. Notice it was actually a squiggly line there too. Now I did this galactose as a squiggly line, but it actually wasn't correct because it was predefined as equatorial when it made its connection. So I'll fix that one. All right, so I'm going to circle that in blue because that was in blue and this one was in red. So lactase comes along and snips it up. Those snips it in just that one spot. Those go off and get used by the body. What happens if there's no lactase? Your body still breaks it down. But instead of lactase, you get your, let's put these mad bacteria. They're just very, I wouldn't say mad, very aggressive. And they fully decompose it. What does that mean? It doesn't neatly get snipped at its glycosidic linkage. It wreaks havoc by breaking it into lots of small pieces. What are those small pieces? Possibly CO2 gas and other gases and acids. So fully decomposed by bacteria to generate excess gas. So that's kind of the common discomfort associated with being lactose intolerant. This is the one time it's not really happy to draw that arrow. So this is only if there's no lactase, because you're missing it. And it is kind of like a interesting, you lose it, you don't use it, you lose it enzyme. So, but you know, there's lots of other good dietary options out there anyway. All right, so how would we describe the glycosidic linkage? We want to be able to look at a disaccharide like lactose and describe that glycosidic linkage. Well, we did say alpha glycosidic linkages are easily digestible by mammals. Is this alpha? If it's so easily digestible by mammals, why is this one hard to digest? Why do we need a special enzyme? Let's take a look. Okay, so we have this, it's simple as saying, look at this top sugar. It has its up group here. Its CH2OH is up because it's a D sugar. Go look at its anomeric carbon, which is making the glycosidic linkage, and draw on the H if you need to, whatever you need to do to see the orientation of that group. It's above the H, so it's also up. Up and up, those are beta to each other. Not alpha. That's why it is not so easy to digest it. That's why you need a special enzyme. Furthermore, what's the numbering on it? It's a beta 1, because we see carbon 1 there. Let's number our primes numbers. 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. I could have stopped at 4 because that's where the linking was happening. It's another 1, 4 prime. So lactose is another 1, 4 prime, just like maltose. Look how different they look though. So notice how it's more like linear looking as a beta, right? It looks like it's almost more planar, whereas here, this has sort of a stair-steppy sort of look to it, right? And that's just the difference of having it beta versus alpha. Let's name the whole thing. Okay, so we're going to end on the glucose. That's our last sugar there. We're going to end on the glucose. We're going to make this our substituent hanging off of the glucose. So it's going to be glucopyranose. Galactopyranosyl as the substituent. So give it its final name, glucopyranose or pyranose. Before I get away from that, let's name that glucose. This is a squiggly line, so I cannot name alpha or beta, but this is up, so I can name it D. Now I'm ready to talk about the other one. It's a galactopyranosyl. Oh, I'm not going to get myself in front there. That's the challenge. I don't like to write backwards, but I'll have galactopyranosyl. Okay. 1, 4 beta, which is what we got in blue up above. Beta 1, 4 prime. Very long names, right? Just for a disaccharide. Okay, so yes, sometimes we can digest beta linkages, but we do need that special enzyme. Okay, another very common, probably the most common in America, disaccharide, our sweetener, sugar, table sugar, sucrose. It's a disaccharide with fructose. So notice the 5-membered ring, it's kind of drawn as a little puckered envelope conformation for you there, but we could have easily also done the Hayworth projection. Let's find the anomeric carbons in there. Oh, that's what the question was. I always like to kind of beeline for those. That helps us understand the linkages. So we're going to label the anomeric carbons in D-glucopyranose, that's the 6-membered ring, and D-fructofuranose, the 5-membered ring, right? So that's the 6-membered ring, and this is the 5-membered ring. So in the 5-membered ring, you look for the oxygen, and you look for the carbons attached to it. Those are going to be, one of those is your anomeric carbon. So that one has no O directly attached again, so it's not the anomeric carbon. This one has 2 O's on the same carbon. That was the anomeric carbon. Same analysis with the top one. Okay, so there's our O, no second O on that carbon. So let's go to the other carbon on the other side of the O. Yes, there's a second O on this carbon. 2 oxygens there. And we'll label that one red. Is there hemiacetal? Let's look for hemiacetal. Or is it an acetal? You look for 2 O's on the same carbon, and that happens at the anomeric site usually. So let's go look here. Anomeric carbon, 2 O's. And if it's an O, if one of them is an OH, then it's a hemiacetal. But if they're both ORs, it's an acetal, right? So OR, OR, acetal. Do that again. O, R, O, R. Another acetal. So there's no hemiacetal present. If there's no hemiacetal, what does that mean? Going back to the equilibrium that it's in, it does not form that aldehyde. It has to go through the hemiacetal if it's in equilibrium with that, then go to the aldehyde. So because it's considered more or less locked once it gets here, this is called a non-reducing sugar. So sucrose is an example of a non-reducing sugar. It would not react with a positive sign on the tolerance test, for example. So the other sugars we were looking at that had all of those terminal squiggly lines for the OHs, that's because that was part of a hemiacetal at the anomeric carbon. Those were reducing sugars. Now, another thing I just want to point out is, yes, I mentioned this hydrolysis. That's what a chemist would do to kind of figure out what the components are, but how does this form? It's the reverse. We lose water to form it. Let's find some water that would come off. Look for our glycosidic linkage. So we know that it's attaching at these anomeric carbons, and if I know that this one is going to be attached at one of the anomeric carbons, we're going to lose the OH of one of them and an H on another. Right? All right, so that is disaccharide chemistry for you. You've got to lose water to form it. You've got to basically hydrolyze it, or you have an enzyme do that for you to separate them. Now we're going to move beyond disaccharides into polysaccharides. There's 3 super common ones made from glucose. Cellulose. Might have heard of cellulose in wood, right? Now let's take a look at it. Is it easily digestible by mammals? Well, you know wood's not. Why? It's not. We have to look at the structure and understand why. What did we know whether it was digestible or by animals or not? It was whether it was a glycosidic linkage that was alpha versus beta. Beta does not lend to easily digestible material usually. So let's take a look at our glycosidic linkage. So we have on one side of our oxygen, we have the CH2OH up. On the other side where the linkage is happening, that's up. So it's beta, right? So every glycosidic linkage, you could see that repeat, beta. And that's just multiple glucose units. Glucose, glucose, glucose. Let's look at the nature of the linkage. Let's number it. 1, 2, 3, 4, 5. 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. So we have that 1, 4 again, right? Beta 1, 4 prime. No, we're not going to be eating that unless you have a special wood digestion enzyme. Okay. We know polysaccharides are something we eat though. So what do they look like? Starch is a good example of one. So we've gone pretty far. We started with candy and other sources of kind of instant glucose. Honey has a lot of sort of fast delivery of energy. And then other sugars take longer to break down. And we might have heard about that all the time, but what does that mean? Starch, sometimes is intended for storage, longer term storage. So starch actually comes in more than one form. We have the amylose versus the amylopectin form. The amylose form is very commonly more dominant in rice. The amylopectin is your potatoes, maybe corn, some of those others. If we look at these, they're both called starch. Why? Well, we said these were all glucose monomer units. So these are all different ways glucose can connect. So what's the difference between the two starches? It looks a little more busy on the bottom, right? So we can be a little more specific about that by numbering 1, 2, 3, 4, 5, 1 prime, 2 prime, 3 prime, 4 prime. I could stop there. We have a 1, 4 prime, and then let's pay attention to our alphas and betas. Up there, down there. Therefore, this is alpha. Alpha 1, 4 prime, over and over and over again. Confirm that with the next one. 1, 2, 3, 4. Yep. I'll do these double primes. Each one is linking at the 1, 4 position. So yes, we like to eat rice. Usually doesn't cause a problem. How about potatoes? Good timing for Thanksgiving coming up. Sweet potatoes, mashed potatoes, corn, all of these things. You can draw this on your napkin, the structure on the napkin at the dinner table. Impress everybody. All right, so let's look at why this is different, even though this is just another polymer of glucose. How is sweet potatoes so different from rice in terms of at least the sweetness and the sugars available? Well, look at how let's number this. This middle is where it looks really funky. So let's start numbering the middle one. So I'm just going to go ahead and call this my 1, 2, 3, 4, 5. But look at my number 5. It's actually connected to another sugar. So I'm going to go ahead and keep numbering until it gets to the new sugar. So that 6th carbon actually connects to it. So let's number it again. We have a 1, 2, 3, 4, 5. So that 6th carbon isn't. So some of the carbons on carbon 6 are attached to another one. So how would we describe this? So we see a 1 in the 6 linkage, and we see 4 bonded to something. So let's count on this ring: 1, 2, 3, 4, 5. So we see a 1 and a 4 linkage. So we have to give 2 names because there's 2 types of linkages. So I'm going to let this one be the primes because we will minimize those. So what kind of linkages do we have? What's the consequence of these double linkages? Everything else only had 1 linkage that we looked at so far. Look at this molecular consequence versus the one before that looked a little more linear, sort of streamlined. So we would describe this as a branched polymer. So this just causes branching. Okay. So just those small molecular changes, that extra glycosidic linkage, makes it a more branched out polymer.